Hello and welcome back to episode 5 of our series on modern operating system design. So far in this series, we have seen how the operating system creates very powerful illusions. Illusions of parallelism, illusions of speed, and illusions of seamless operation, right? So in the last episode, we looked at how the CPU decides which process should work when, and we also looked at how parallelism is created by the operating system using processes and threads in previous episodes. So now comes an even bigger illusion. Every program believes it has its own private contiguous memory starting neatly at address 0. Even though in reality memory is shared, fragmented, it is limited and constantly changing, the process always sees its memory as a contiguous set of memory blocks. So today's episode is about how OS pulls off this trick. This is called memory management. So if you have not seen the previous episodes, do go through my previous episodes. There's a lot of interesting stuff I have covered. And of course, please like and subscribe this video if you seem to be enjoying this episode. Now let's get into today's topic, which is memory management. So let's start with the topic of address spaces. Memory has a name and not really a place. What do we mean by that? Is when a program executes an instruction that accesses memory, it does not refer to the physical RAM directly. Instead, it operates within an address space, a series of labels or names or numbers that are given to the set of memory locations that can be addressed, and the process that is executing works with the address space that is given to it. It has no idea of where the physical memory is, where it's coming from. It's a conceptual range of addresses that the program is allowed to use. So an address space defines what memory locations a program can reference. It also defines how these references are isolated from other programs, what protections apply, all of those things. So to the program, the address appears absolute and meaningful. To the operating system, they are merely symbolic names that must be translated into real location. So this is the distinction that's fundamental to memory management. An address that a process sees is not a location, it is a label. So by interposing between the addresses and physical memory, the operating system gains a little bit of control. It can decide which memory belongs to which process, it can prevent illegal access, it can enable multiple programs to coexist safely. A lot of these things can be done. So address spaces are the foundation of process isolation. Without them, a single faulty program could probably corrupt the entire system. Now let's take this address space concept a little bit forward into virtual memory. This is the illusion where the process feels that it has a lot of memory available to that. So once memory addresses are treated as abstractions rather than physical location, so instead of saying that if you have physical memory addresses starting from 0 going to let's say 10, instead of giving access to the same physical location, what the operating system does is it brings in a layer. It maps a set of logical names, logical labels. Maybe they're also, by coincidence, they are also 0 to 10, and the process feels like it's actually accessing memory location 0 all the way to 10. In reality, that's not what happens. So these are labels that the operating system has given to the process. So when the process accesses something at let's say memory location 3, the operating system will take the label, try to figure out where memory location 3 for this process is actually stored on the real physical memory. Maybe it is in location 6. It reads data from there and gives it back to the process. So what happens is the process believes it read memory from let's say memory address 003. But in reality, it could have come from 006. So this mapping gives the operating system a lot of control on which memory is allocated to which process. This also kinds of enables the operating system to play with the available limited memory and create an illusion of having a lot more memory. So if I can create labels from 0 to 100, but in reality I have hardware memory locations from 0 to 10, as far as the process keeps getting data back whenever it reads a memory location, as long as it reads let's say memory location 99 and gets back its whatever data it was expecting to read from that location, the process or the program doesn't care where it came from. Now the operating system has little more freedom to manage where the 99th location is stored, because it has only 0 to 10 available spots to store random access memory. Suppose it also starts extending this into the disk hard drive and starts putting some data somewhere else, and as long as it can do this mapping, do this jugglery and give you or give the process the right data, The process doesn't care where it came from. So in reality, the process believes it has like GBs of process space or memory locations allocated for it. But in true reality, that's not how it is. It is spread out across different physical locations. Maybe some of it is in RAM, some of it is on the hard disk, all of those things. So this is where virtual memory comes in. So once memory addresses are treated as abstractions rather than physical location, the operating system can pretend that more memory exists than is physically available. So this idea is called virtual memory. So in a virtual memory system, each process believes its entire address space is in the RAM, but in reality it's not. Only a subset of the memory is present at any given moment. The rest of it is on a secondary storage, such as a hard disk or a solid state drive or whatever is the hard storage mechanism available to the operating system. So memory is loaded on demand. When a program accesses a part of memory that is not currently in RAM, the operating system transparently fetches it from the disk and resumes execution. The process never realizes what happens. So if you have 10 processes running, if you have a 16 GB RAM machine, and if each of the process is given 4 GB of memory address space, then you actually need 40 GB, right? But you have only 16 GB of RAM available on your machine. So what the OS does is it creates this virtual memory and allocates these labels for the memory locations and gives it to each process. So from the program's perspective, nothing unusual occurs. It has a process memory space, addresses, it can keep accessing those addresses. So virtual memory transforms memory into a managed resource rather than something with very fixed constraints and limits. So programs much larger than the available physical RAM can run easily, and it's much more efficient to share memory among different processes. And there is also a lot of strong isolation, fault containment, all of those things. So conceptually, your RAM becomes a cache or a cache, not of files but of the address space itself. So that's how virtual memory extends your limited physical RAM. That naturally leads us into another topic called paging and segmentation of memory. So to manage memory efficiently, the operating system must divide it into manageable units. So there are a couple of major approaches like segmentation and paging. Segmentation basically divides memory according to the logical structure of a program. So typically you have code segment, data segment, stack segment. If you have not looked at the C programming series on BitLearn, go ahead and check it out. You will actually figure out how a program is allocated different blocks of memory for its use. So if I write a hello world program and I load it into memory, what happens is a chunk of memory is given for the instructions, the code, a chunk of memory is given for the data, which is the variables and all the static things that are declared, and another chunk of memory is available as a stack. All of this together is the process space or the memory addresses that are available for a process. So that is a segment. So that is how segmentation comes into picture. Each process gets a segment. So each segment has a base address, a size, and an access permission. So we have code segment, data segment, stack segment, heap. So this approach aligns well with how programmers think about programs also. Code is separate, it is distinct. We don't have to rewrite that or change that dynamically in real life, as long as the process is running. And data is different. Some of them are already initialized. You have fixed space, and then we have stacks and heaps. So please do check out the C programming series where we talk about stacks, heaps, and how data is organized as a neat little house. Go check it out. Thank you. So now let's look at how segmentation introduces its own complexity. Because segments vary in size and memory also becomes fragmented over time, finding contiguous free regions becomes increasingly difficult. So this is where paging comes in. So if you have a memory segment that is 4 GB in size, I may not be able to provide a contiguous set of memory allocations for 4 GB of memory. So what I may end up doing is I may split it into pages. I may split that into pages of, let's say, 512 MB. So I may give you a set of 8 512 MB chunks that will give you 4 GB in total. So that is how paging comes in. It takes a very different approach. Memory is divided into fixed size blocks called pages in virtual memory and frames in physical memory. They are more or less similar. So pages are uniform and they can be swapped very easily. So what happens is if you start executing a set of instructions, which are, let's say your program is 32 GB in size and you have only 4 GB of RAM available, and the code is loaded onto a set of pages. as you start executing through the instructions, once you are done with the 512, the instruction at the 512 MB position, what the OS can do is swap out that page and bring in another page from a frame in physical memory. So this is called paging. Very similar to segmentation. So segmentation is about dividing available memory. Paging is about how do we, cache or take these memory chunks and have it spread out between physical RAM and the actual hard disk or whatever is the secondary storage you have. So paging offers several advantages. So one is it eliminates any external fragmentation, it simplifies allocation, and most OSs overwhelmingly rely on paging as their primary memory management mechanism. It is sometimes combined with segmentation concepts for protection, but paging is clearly very common across any operating system. So the trade-off is clear. Paging favors efficiency over how we rely only on intuition in segmentation. When I say intuition, if you look at segmentation, we are talking of cleanly dividing a chunk of memory into code, data, and what else? Stack, heap, those kind of things. That still is used, that is available, but paging is what is primarily used to make more memory available for the process. So let's look at how page replacement occurs. So physical memory is finite. So when all the frames are occupied and a new page must be loaded into memory, what the operating system does is it has to remove something. So if I have 16 GB of RAM, and let's say my program is using all the 16 GB of RAM, and I have some more data that needs to be loaded, where do I put it in RAM? So I have to make a decision. So this decision is governed by page replacement algorithms. So this is a decision that is done by algorithms which look at whether I can replace this particular page or whether I can replace this particular page, and the decision is based on some criteria. So let's look at the least recently used criteria, which is LRU. The principle behind LRU is straightforward. Pages that have not been used recently are less likely to be used again in the near future. So you have loaded the entire program and there is a page that you have never addressed so far in the program. So chances are that's a page you may not need at all. So that is the one that might get replaced when you want to bring in a new set of instructions or data from the secondary storage. So in theory, LRU kind of approximates the optimal behavior, but when implementing it, it becomes a pretty expensive proposition. So what LRU illustrates is a recurring pattern in operating systems. The idea that the best theoretical solution is often impractical. So what we do is they come up with more and more algorithms. So there's one more called the clock algorithm. It offers a compromise between accuracy and efficiency. So pages are arranged in a circular list. So each page has a reference bit indicating if it was used or not, and a pointer sweeps through the list like the hand of a clock. If a page has been used recently, it is given a second chance. If it is not, it is selected for replacement. So that way there is a little bit of rotation. There is also LRU, so it's a mixture of things. So the clock algorithm sacrifices precision of speed and simplicity, and it kind of tries to balance everything. So this is how operating system design favors solutions that work well instead of something that's fast enough on paper or just fast enough in real life. So this is how operating systems have to make decisions. So as a designer of an operating system, we need to figure out different algorithms that might give us the best balance of simplicity, efficiency, those things. So let's take a little more deeper insight into how memory management is not primarily about storing data. So far we said that memory management is used through paging, through virtual memory, and all of these concepts to basically make a larger superset of data or memory space available to a process. And that might give the idea that this is all about storing data. Actually, it's not. So there is a lot more behind that. So there is constant negotiation between how much of the hardware limits can be extended for each process. How do we make more things available? And there is also a lot of logic and design that goes into protecting different processes. So because there is this 16 GB of RAM example that I talked about. So that is a common area that is used by all the processes. So when a clock comes into the foreground and it is working, it has access to its, let's say, for simplicity, this 16 GB of RAM. Once that process is swapped out, that 16 GB needs to be swapped with the data for a browser. So similarly for something else, for the editor. So there is also a good amount of thinking that has to go into how do we provide security among these processes, how do we make sure that there is no overlap and breaches in terms of memory access. So when memory management works well, it is invisible. We don't even know that it's there. It just works. But when it fails, the system starts slowing down. We start seeing disk thrashes, which is more less frequent today because disk thrashes were more common when we had mechanical hard disk, but today we have mostly SSDs, and we also have total system collapse. That's also a possibility. So understanding memory management is understanding how the operating system reconciles reality with the expectations that the processes have. And that is why abstraction is the most powerful tool in system design. So that that is basically what memory management is all about. So I'm going to take a pause here and we'll move on to the next chapter in the coming episode. Meanwhile, if you like this one, do like, subscribe, and make sure you put some comments down there. I'm pretty sure if you have come up to episode 5, you've been following the previous episodes. So let me know what you like and what you don't like. So with that, I'll see you in the next episode. Thank you for watching.